So screen is visible to everyone. Okay.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. Thank you. So everyone, please unmute your. Sorry, mute yourself. Uh, so I will start now. So hello everyone. Good evening to all. My name is Abhishek Pandey. I am a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. Today we are going to discuss about week 4 assignment. So let us start. So this is the first question. Uh, so the first question is, let D denote the unit disk, okay, and del D denotes the boundary of unit disk. Which of the following are true? So the first option is, if for any W belongs to C, we define dW, okay. So this dW is a disk, center at W and radius 1. Okay, so mod z minus W is less than 1. So we need to check this one. Modulus of e to the power z is less than equals to this for any z dW. Okay, so any z which is in dW will satisfy this inequality. Okay, now this is greater than this one. Okay, and this is always greater than this one. So finally we are getting mod z is less than 1 plus mod w. Okay, and as we know, real part of z is less than equals to mod z. So now once you calculate modulus of e to the power z, you will get modulus of e to the power x plus iy equals e to the power x into e to the power iy. Okay, so this will be basically, this modulus is nothing but 1. Okay, so this is nothing but e to the power real power z, and real part of z is less than equals to mod z. So you will get less than equals to e to the power mass z, and mod z is nothing but less than this. So you will get modulus of e to the power z is less than equals to e to the power mod w plus 1. Okay, so the first option is true. Now let us look at the second option. So let f such that d to c be a holomorphic function. Suppose that omega is contained in d is open such that omega closer intersection boundary of d is equals to phi. Okay, then f is bounded on omega. This is the question. Okay, so now what you can do, so let f such that d is to c be a holomorphic function. So basically d is unit disk. Let me denote like this. So I will denote unit disk. So I will denote unit disk as like this. Okay, so this is a holomorphic function, and omega is a subset of d which is open such that this omega closer intersection of omega closer with the boundary of d means the unit circle is phi. So basically this omega closer is in d itself. Okay, and since omega closer is compact, so f is bounded on omega closer and hence on omega. Is it clear? So basically, since boundary doesn't meet, okay, omega closer doesn't meet the boundary, okay. So basically, omega closer is in D itself, and since omega closer is compact and f is holomorphic, so it is bounded on omega closer and hence on omega. Okay. Now let us look at, so this is also true. So this is also true. Now, if f is a holomorphic function on omega, where d closer is a subset of omega, and such that f is identically equals to 0 on boundary of d. then f is identically equals to 0 on D. Let us look at this option. So let f be a holomorphic function on omega, where, so D closure is contained in omega, okay, such that f is identically equals to 0 on boundary of D, okay. As we know that D closure is nothing but D union boundary of D, and it is contained in omega, okay. So this implies boundary of D is also contained in omega. Thus zeros of f has a limit point in omega. So as you know, if f is a holomorphic function in a domain and its zeros has a limit point in that domain, then f is identically equals to 0 on omega. So in particular, f is on D. F is identically equals to 0 on D. Okay. So this is also true. Suppose that S is the open unit square given by this, and del S is the boundary. If two entire function agrees on del S, then f and z agrees everywhere on S. Okay. So this is also identity theorem. So let f and z be two entire function which agrees on del S. Okay, boundary of S. So now consider hz is equals to fz minus gz. Now hz will be 0 on boundary, and h is also entire. H is also entire. Okay. So now since h is identically equals to 0 on the boundary, means h is identically equals to 0 on C, because this has a limit point in C. Okay. So in particular, fz is equals to 0 for all z belongs to C. Thus fz equals to 0 for all z belongs to S. Okay. Is it clear to everyone? Someone please respond. Hello?
Yes, sir.
Okay, fine. Now let us look at the next option. So this is also true. So let f be a holomorphic function on omega, where omega contains D closure. Then this we have to check. Okay, like infimum of z belongs to D modulus of fz equals to infimum belongs to z belongs to boundary. Okay, so this we are taking the infimum on the boundary. This one. Okay. So this, for this we can take a counter example. Okay. So basically you take fz is equals to z. Now as you can see in, and D is your unit disk. Okay. So as you can see, infimum of mod of fz equals to 0 in unit disk. Okay. But infimum of mod of fz on the boundary is 1, which is not equal. This is not equal. Sorry. This is not equal. Okay. So this option is not correct. Now let us look at the last option. Let f be a holomorphic function on an open connected subset omega of the complex plane containing D closure, means unit disk closure. Okay. Suppose that f does not vanish on boundary of D. F does not vanish on the closure of D, then this we need to show. So this is some kind of minimum modulus theorem. Okay. So we will prove this one. So first recall the maximum modulus theorem, which says that let G be a bounded domain in C, and suppose f is a continuous function on G closure, which is holomorphic in G, then this maximum over the closure is attained on the boundary. Okay. So since, as you know, it is written that f is non-zero, f does not vanish on D closure. Okay. So f is holomorphic on omega such that fz is not equals to 0 for all z belongs to D closure. So we can define gz equals to 1 upon fz on D closure. Now G is holomorphic in D and continuous on D closure. So it satisfies the condition of the maximum modulus theorem. So maximum of this will be attained on the boundary. Okay, so maximum of this is basically infimum of fz because it is 1 upon fz. Okay, so infimum of z belongs to D closure is nothing but infimum of z belongs to boundary. Okay, so this one is also true. Now let us move towards the second question. So second question is for on the harmonic function. So the first question is, let uxy is this. So we need to check whether it is harmonic on this D1. So basically, this is a disk centered at 1 of radius 1. Okay. So let us check this one. So what we will do, we observe that uxy can be rewritten like this: x minus 2 whole square plus y square. Okay. Now, so this we can write it as, so, x minus 2 upon x minus 2 square plus y square. Okay, so basically to check harmonic function, we have uh, lot of tools we can use. Like we can go by the definition, like we can check whether it is whether Laplace is 0 or not, Laplace equation of this, like uxx plus uyy equals to 0 or not. Or we can convert it into polar form and check the Laplace equation in polar form, it is 0 or not. Or we can check whether this uxy is real part of some holomorphic function. Okay, if it is so, then this is harmonic. Okay, so I will use the third tool, like I will show that it is a real part of some analytic function. So this is nothing but real part of x minus 2 upon x minus 2 whole square plus y square minus iota into y upon x minus 2 whole square plus y square. Okay, so this is clear. Real part of this is nothing but this one. Now this we can write it as real part of x minus 2 minus iy upon x minus 2 whole square plus y square. Okay, so this is basically real part of this. We can write it as z minus 2, okay, upon z minus 2 uh, bar upon z minus 2 whole square. Okay, so this is the real part of 1 upon z minus 2. Okay, and our domain is z minus 1 upon, so z minus modulus of z minus less than 1. Okay, so 1 upon z minus 2 is holomorphic in this one, isn't it? So 1 upon z minus, sorry, 1 upon z minus 2 is holomorphic in z such that mod z minus 1 is less than 1. Okay, thus u is harmonic because it is a real part of a holomorphic function. Since it is a real part of a holomorphic function. So this one is clear to everyone? So is this clear to everyone? Please let me know.
Yes, sir.
Okay, fine. So this option is correct. Now the second option is let f and z be two holomorphic functions defined on an open connected subset omega such that real part of f is equals to real part of g for every z belongs to omega. Then fz equals to zz for every z belongs to omega. So let us see. So basically you define a new function, okay, hz is equals to fz minus gz, okay. So h is also holomorphic, in omega, okay, and real part of sz is 0 for all z belongs to omega. So basically h dash z will be 0, okay, because s just, so h dash z is nothing but del by del x of real part of z plus del by del x of. So real part of sz is 0 and h is holomorphic, okay. Hello, is it audible?
Yes, sir, it's audible.
Okay.
Yes, yes, sir.
Okay, okay. So h dash z will be 0 for all z belongs to omega, and since omega is a domain, we have h is constant, okay. So basically h z is equals to k for some k belongs to c. Also real part of k is equals to 0, that is k is purely imaginary, okay. So basically k is something k1 plus I k2, and since we know that real part of k is 0, so basically k1 is 0, so k is basically purely imaginary, okay. So basically fz is equals to gz plus k, isn't it? fz is equals to zz plus k, so this option is not correct, okay. So this option is not correct. So similarly, this option is true because just now we have shown that fz minus gz is purely imaginary constant on omega. The harmonic conjugate of a given harmonic function u on omega is unique. This is also not true. Let us see. So we will prove this theorem that harmonic conjugates are unique up to adding a constant. Okay. So basically, let V and W are two harmonic conjugate of U. Okay. So yeah. First recall that harmonic conjugate means U plus IV is holomorphic in omega, whatever domain is given. So then I W minus V is equals to U plus I W minus U plus IV. So this is holomorphic because of the difference of two holomorphic function. Okay, and since this is purely imaginary and holomorphic, it must be a constant. Okay, thus W equals to V plus A for some A belongs to C. Okay, so this is also not true. Now let V be a harmonic conjugate of a function U such that U minus V is constant, then U is constant. So this is true. So let V be a harmonic conjugate of U on omega such that U minus V is constant. So F equals to U plus IV is holomorphic since V is a harmonic conjugate. Similarly, IF is also holomorphic. Now you add F plus IF. This will also be holomorphic because the sum of two holomorphic function is holomorphic. Now U minus V is K1 according to the question. So F plus IF will be constant. Okay. And this implies U plus V is equals to K2. K2 belongs to C. By equation 1 and 2, we have U equals to K3. So U is also a constant. So basically K3 equals to K1 plus K2 by 2. Okay. So U is also a constant. So this is option is true. Okay. Now let us move towards the third question. So third question is a very important question. It is uh, it is on Mobius transforms. Okay. So let GL2C denote the group of all invertible 2 cross 2 matrices. In particular, observe that if alpha is equals to A, B, C, D belongs to GL2C, then basically C comma D cannot be 0 comma 0, because determinant of alpha is nothing but AD minus BC. So if BC is 0, uh, sorry, C or D is 0, both are 0, determinant will be 0. Okay, so it will not be invertible. Okay. If alpha is as above, then we denote the Mobius transformation alpha dot z equals to az plus b upon cz plus d. Okay. So now let us look at the first option. So first option is saying if alpha comma beta belongs to GL2C. So first we need to check alpha dot beta dot z. Okay. So this will be equals to alpha dot, this will be, so let alpha is equals to a1 b1 c1 d1 and beta is equals to a2 b2 c2 d2. Okay. So alpha dot beta dot z will be a2z plus b2 upon c2z plus d2. Okay. Now this will be, so here I will write, so this will be a1 into a2z plus b2 upon c2z plus d2 plus b1 upon c1 a2z plus b2 upon c2z plus d2 plus d1. So this is nothing but a1 a2z plus a1 b2, okay, plus b1 c2z plus b1 d2 and c1 a2z plus c1 b2 plus d1 c2z plus d1 d2. Okay. So now this is nothing but a1 a2 plus b1 c2 into z plus a1 b2 plus b1 d2 upon c1 a2 z, oh sorry, c1 a2 plus d1 c2 z plus c1 b2 plus d1 d2. Okay. So this is nothing but what we can write a1 a2 plus b1 c2 comma a1 b2 plus b1 d2 c1 a2 plus d1 c2 c1 b2 plus d1 d2 into z, alpha dot z. Okay. Now you can see that this is nothing but alpha into beta. Okay. This quantity is nothing but alpha beta dot z. This is nothing but alpha into beta. So alpha into beta is this. Okay. So this option is true. First option. Now let us look at the option B. So it is regarding 2 alpha dot z. So 2 alpha dot z is nothing but, so 2 alpha will be, so let alpha is equals to a b c d, so 2 alpha is nothing but 2a 2b 2c 2d. Okay, so 2 alpha dot z will be 2a z plus b upon 2c z plus 2d. So this will be nothing but az plus b upon cz plus d. This will be nothing but alpha dot z. Okay, so this is wrong. Okay. Okay, so let us look at the third option. Up to this, everything is clear to everyone? Hello? Up to this, is it clear?
Yes, sir.
Okay, okay, fine. So let us look at third option. So now the third asking is like it is a well-known result. So if in particular alpha belongs to SL2R, that is collection of all matrices with real entries and determinant 1, then imaginary part of alpha dot z is positive if and only if imaginary part of z is greater than 0. So basically it is saying, so now the third option, so let alpha belongs to SL2R, okay, that is alpha is equals to A, B, C, D, where A, comma B, comma C, comma D belongs to R and AD minus BC basically 1. Okay, so now it is saying, so basically alpha dot Z is nothing but AZ plus B upon CZ plus D. So it is saying that now H plus is the upper half plane, Z belongs to C such that imaginary part of Z is greater than 0. So it is saying that the question is regarding the map, the image of H plus. Okay, so the question is alpha dot Z maps H plus onto itself. Okay, under all these conditions where alpha is this. Okay, so this is the question, isn't it? This is the upper half plane, then again the image is also in upper half plane. Okay, alpha dot z. Is it clear, this thing? Hello?
Yes, sir.
Okay, good. So this theorem I will recall, with that one it is clear. So the Mobius transformation Az plus B upon Cz plus D maps upper half plane onto itself if and only if and only if these two conditions A comma B comma C comma D belongs to R, and second one is AD minus BC is positive. Okay, so with this theorem it is clear, isn't it? Like the alpha which we are choosing, obviously it is positive. Okay, AD minus BC, so it will map H plus onto itself. Okay, so with this theorem it is clear. This theorem is quite a standard theorem, you can find in any book like Conway. So book reference I will write here. Book reference I will write here. So Conway or Bruce P. Palka. Any standard book will give this theorem. Bruce P. Palka. Okay. So with this theorem, this is also true. Now for option D and E, I will recall a very basic concept, like how to relate algebra with this kind of thing. Algebra in the sense group theory. Okay. So what I will do, what I will recall group action. Okay. So let basically what is the option C and D. Basically, I will relate it to stabilizer and orbit, okay, under group action, and the transitivity of the group action. Okay. So first, let us see the group action. So let X be a set and G be a group. We say that G acts on X if there is a map G dot X to X satisfying 1 dot X equals to X for all X belongs to X, and G H dot X is equals to G H dot X, where for every G comma H belongs to group and X belongs to set, where 1 is the identity of G. Okay. So you guys are everyone is familiar with this group action. Okay. So given such an action, define a relation on X, okay, by X is related to Y if and only if there exists a G belongs to group such that Y is equals to G dot X, okay. Now you can check that this is an equivalence relation on X. Now orbit of an element is this, the definition of an orbit, okay. So basically this is all the collection of G dot X, okay. And stabilizer is nothing but collection of all the elements which is such that G dot X is equals to X. Okay. Now this is the important definition. An action of a group G on a set X is said to be transitive if it has a single orbit. That is, for any two point X comma Y belongs to set X, there exists element G belongs to the group such that Y is equals to G dot X. So this definition is clear to everyone, this definition and group action. This is very basic in the group theory. I mean, you can find this in standard book. Is it clear? Because understanding of this definition is important to relate the group action with this complex kind of thing we are doing. So is it clear to everyone? Anyone please respond? Hello?
Yes, sir.
So this is clear, na?
Yes.
Okay. So now SL2R acts on the upper half plane. Okay. So this is nothing but upper half plane. So how it acts on upper half plane? So basically, you take alpha in SL2R and you apply alpha dot z is equals to az plus b upon cz plus d. So this will be again in H plus, okay, like the way we have proved earlier. Okay. Now let us look at the options C and D. Okay. So what is the first? So what is the option C? Okay. So option C is, suppose that imaginary part of z is greater than 0, then there exists an alpha belongs to SL2R such that alpha dot I equals to z. Okay. Okay. Now let us look at the option D. This is saying you take any point 2 point z1 zt in upper half plane, then there exists an alpha belongs to SL2R such that this one. Doesn't it looks like the transitivity of group on a set, like group G acting transitively on a set? This is the definition, no? Like for any 2 points G x1 comma x2 in the set, there exists a group element G such that G dot x1 equals to x2, isn't it? So basically we have to, for option D, we have to check whether SL2R acts transitively transitively on upper half plane. Okay, this we need to solve. Okay. So option C and D I will start now. So suppose imaginary part of Z is 0. So our claim is there exists an alpha SL2R such that this satisfies. So this is easy to construct such kind of alpha. So let Z equals to x plus y, where y is greater than 0. Now take alpha equals to root y, x upon root y, 0, 1 upon root y. So you can check that alpha of I is nothing but x plus iy. Okay, so basically alpha dot I is nothing but uh, I under root y plus x, okay, upon root y upon 1 upon root y. So this will be x plus iy. Okay, so done. Now the inverse of alpha will take z to I. So option C is correct. We have constructed an alpha such that alpha dot I is z. And observe that inverse of alpha will take z to I. So our claim is SL2R acts transitively on S plus. That is, for every Z1 comma Z2 belongs to S plus, there exists alpha belongs to SL2R such that alpha dot Z1 equals to Z2. So let alpha 1 belongs to SL2R such that this, so a Z1 goes to I, okay. This will exist, basically so basically alpha 1 is the inverse of alpha, okay, this alpha, okay, and this will also exist alpha 2 so alpha 2 belongs to SL2R such that alpha 2 I is equals to Z2. Basically this is sending I to Z2. Now what to define alpha equals to alpha 2 alpha 1. So alpha dot Z1 will be alpha 2 alpha 1 dot Z1. This will be alpha 2 dot I. This is equals to Z2. So alpha dot Z1 equals to Z2. Hence SL2R acts transitively on S plus. Okay. So option C and option D both are true. Now this question is also easy. So this is also true. Let us see. So if alpha belongs to SL2R is such that alpha dot I equals to I, then there exists a real number theta such that this happens. Okay. So let us see. So let alpha belongs to SL2R such that alpha dot I equals to I. So this is nothing but, so let alpha is equals to A, B, C, D, where A, B, C, D belongs to R and AD minus BC is nothing but 1. Okay. So AI plus B upon CI plus D equals to I. This will be, this will give AI plus B is equals to DI minus C. Since alpha belongs to SL2R, this will happen like this is the definition. So after comparing the real and imaginary part, you will get alpha A equals to D and B equals to minus C. Okay. So now put this A equals to D, B equals to minus C here. AD minus BC equals to 1. So you will get AP square plus BP square equals to 1. Okay. Now A comma B is a point on the unit circle. Okay. So basically A plus IB belongs to S1. Okay. So basically A plus IB is of this form. Okay. For some theta belongs to this. So A is cos theta, B equals to sin theta. So alpha is this. Okay. So this is what the question asks. So this option is also true. Now let us look at the fourth question. So up to this, everything is clear. If any doubt, you can ask me or write in the comment section, the chat box. Is it clear to everyone? Is it clear?
Sir,
Yeah. Any doubt? Hello? Hello? So if no doubt, let us look at the question 4. So let Z1, comma Z2, comma Z3 belongs to C be non-collinear points. Okay. And let gamma be the unique circle passing through Z1, Z2, Z3, starting and ending at Z1. Let phi be the Mobius transformation that maps this to 1i minus y minus I minus 1, 1i minus 1 respectively. So defined by phi o gamma, the curve defined by this, then what is the value of this one? Okay. So 1 upon 2 pi, this is the length of curve. So this phi o gamma is length of phi o gamma. Okay. So basically this is the circle starting at Z1 and ending at Z1. Okay. And phi sends Z1 to 1, Z2 to I, Z3 to minus 1. So as you can see, 1, I minus 1 are non-collinear. Okay. And the fact you know that Mobius transformation maps circles in C infinity onto circles in C infinity. Basically circles in C infinity either a straight line in C, either a straight line in C L union infinity or a circle in C. Okay. So this Mobius transformation will send this circle either to a line or a circle, which will pass through 1 I and minus 1. But since these 3 points are non-collinear, so the only option we left is circle. Okay. So now this phi o gamma is nothing but a circle. So as you can see that phi o gamma is again a circle centered at 0 and radius, what is the radius? 1. Therefore, what is this one? This will be 2 pi r. R is 1. So 2 pi upon 2 pi equals to 1. Is it clear? So before going to solve question number 5, let us look at the question number 6. So basically, gamma is defined in this interval to C given by this. So we need to find the length of gamma. Okay. So basically, length of gamma is defined as like this, the Euclidean length, and this will be integral 0 to 2 ln 10, basically log 10 base e, gamma dot t dt. Now this is just an easy calculation, so this you will get 99. Okay, this is an easy calculation. So the answer is 99. Now let us look at the fifth question. So it is just based on the curves, like length of the curves and reparameterization, how it behaves. Okay. So let us look at the first option. So suppose gamma 1 such that AB to omega is a curve and gamma 2 is a reparameterization. So what is the meaning of reparameterization? So gamma 2 is said to be the reparameterization of gamma 1 if there exists a continuous onto a non-decreasing function h such that, so h is defined from 0 comma 1 to a comma b such that gamma 2 can be written as the composition of gamma 1 with h. Okay. So by the definition you can see image of gamma 2 is basically image of gamma 1. So basically then the image of gamma 1 and gamma 2 in omega coincide. So this is correct. Representation change the length of the curve. This is obviously wrong. let us see. So as you can see this one, so this you can see that the length of gamma 2 is basically the length of gamma 1. Okay, so basically we are just changing the interval, okay, on which gamma 1, gamma 2 defined by the reparameterization. Okay, so basically we can say it as a change of variable. Okay, reparameterization of a curve basically can be seen as a change of variable. Okay. So this is also not correct. Let gamma 0 comma 1 to c be the curve defined by gamma t equals to 1 for all t belongs to, then basically the length of gamma equals to 1. This is not correct. Length is basically constant curve, it is 0. Okay, so length is basically 0. Now let us look at the D option. Any curve is uniquely determined by gamma of 0 and gamma dot t for every t belongs to 0. So this is also correct. Let us see. So let these gamma be another curve. So let these are two curves such that this holds and this holds for all t belongs to 0, 1. And since this holds means this is nothing but they differ only by a constant. Okay, these two curves differ only by a constant. Okay, and since they gives the same value at 0, we will get k equals to 0. So basically these two curves identically equals to each other on 0 comma 1. Okay, so this is also true. Now this option by definition also, so this is the real part and imaginary part of a curve gamma t. Then gamma is continuously differentiable if and only if both are continuously differentiable. So basically gamma t is said to be continuously differentiable if gamma dash exists and continuous. So if it is continuous, if gamma dash t exists, so basically gamma dash t is nothing but plus I delta dot t. So if gamma dash t exists means if and only if this exists. And gamma dash t is continuous, gamma dot t is continuous if and only if this is continuous and this is continuous. So this option is also true. Now suppose last option. So last option is also true. So basically this is the like adding of two curves. How we will add the two curves. Suppose gamma and gamma 2 be two curves such that the terminal point of gamma 1 is the initial point of gamma 2. Then the length of gamma 1 plus gamma 2 is basically equals to length of gamma 1 plus length of gamma 2. So basically it is based on how we define. So this is gamma 1, okay, and as you can see the terminal point of gamma 1 is basically the initial point of gamma 2. Okay, so the addition of curve, like addition means this curve, so this whole curve from here to here, let us denote it as gamma 1 plus gamma 2, let us say gamma. Okay, so this is defined like this. From t equals to 0 to 1, it is gamma 1 t, and in between this, it is gamma 2 of t minus 1. So once you calculate the length, this will, so you will separate the interval 0 to 1, this integral, and 1 to 2, this integral. So once you take t minus 1 between 1 to 2, this will be in 0 to 1 only. So once your t is in between 1 to 2, t minus 1 is in between 0 to 1. So this is again the length of gamma 2. Okay, so this option is also correct. So we are done with the assignment. If you have any question, feel free to ask. Okay, any question, anyone? Hello. Anyone have any question regarding whatever
No,
we
sir.
did? Yeah. Hello, who is this?
No question, sir.
Okay. Okay, so if there is no question, I will close the meeting and we will meet till next Friday. Okay. So everything was clear, like group action and those things. How a group acts transitively on a set. So basically, this keep in your mind that SL2R acts transitively on this upper half plane. Okay. So this group action is also useful in defining Riemann surfaces. Okay. So this will come later. So everything is clear, I think. Okay, so I will close the meeting now.
Thank you, sir.
Yeah, thank you.